they're going to tie me down to this microphone, and if they tie my hands, then I'll be totally mute, or moot, either one. Yeah, I was going to point out the irony that I want to talk about the sun to people in a dark room on the one day and the last month when there's sun outside. So at the end of the time here, on the floor you see this box right here. In the box is a set of eclipse glasses. Now I don't want you to keep them forever and ever, but if you want to take them, go out into let's hope the clouds haven't come. Put them on, and the way you use them, in case I forget to mention later, is you line yourself up so you know the sun's right up here. You put the eclipse glasses on, and then you look up, right? We don't want to be looking at the sun and then put the eclipse glasses on. That's not the best way to do it. Having said that, I just looked at the sun myself, naked eye, that is, with one of these, and there's nothing much to see. Sometimes there are sunspots that are big enough to be seen with the naked eye, but we're nowhere near that stage yet. So, but it's still somehow kind of surprising when you look up and see just this ball, and it looks a lot like a ball, rather three-dimensional almost, when you use these glasses. So, help yourself to that at the end of the time. Got this here, as is always the case. Any good preacher will tell you that if you have to give the sermon title early in the week, what comes out the day of the sermon may be totally different. This isn't quite that bad, but as I was getting this ready, I thought, no, what did I tell him I was talking about again? And I saw this business about causation and correlation, and I thought, well, we'll get to that. But my main goal, frankly, is just to excite you a little bit about the sun, about the kinds of things that happen on the sun, and about the connections between the sun and the earth. Some of them are quite obvious. Some of them are less obvious. Some of them are old hat, probably to most of you. A few of them are surprisingly current and controversial, and we'll touch on those as well. So, in particular, things that connect to climate change. So, let's move on. This is all the images, all but two, I think, of the images come from various NASA sources. So this is an actual image from space of the Earth. In some ways, this kind of exaggerates the thickness of the Earth's atmosphere because of the really great shadows that the storm clouds are producing. Right as they're right along the terminator there of the day-night boundary, you find the shadows are the longest, and so it makes them, that one storm cloud in the upper left there is really amazing. Mostly we think of the atmosphere if I usually draw on the board in the class, if I draw the biggest sphere, biggest circle, I can draw on the board and say, all right, in that chalk line is not only the entire atmosphere, but the depths of the Marianas Trench. Virtually any place people have been other than in spacecraft is included in that one chalk line. So when we talk about the interaction between the sun and the Earth, and particularly the sun and the Earth's atmosphere, we're really talking about a very brittle, thin layer around the Earth that's experiencing most of what I want to point out when we get to that part. Okay, so what are the different ways that the sun can communicate with the Earth? It's a very one-sided relationship. The sun pretty much just tells the Earth, and the Earth reacts. The sun being 1,000,000 times the volume of the Earth, so that you guess who wins. The sun, of course, we're gravitationally bound to the sun. We go in an orbit. I joked with Emrys that we're going to take up a collection for a wireless mic after this. Of course, the thing that we're most immediately familiar with is the interaction of light from the sun with the Earth, and that's maybe the dominant thing. We all have somewhere an idea that if it weren't for that, we wouldn't be here. But there's a couple other ways that the sun interacts with the Earth that turn out to also be very important for particular things. There's a particle stream coming off the sun constantly, and we'll get into the numbers for that in a little bit, called the solar wind. It's an extension of the outer layer of the sun, and it comes out to the Earth, and there's a constant interaction between that stream and the Earth. And then the third general category would be the magnetic field of the sun, which is also wrapped up in this solar wind. There are events that bring complicated, twisted shapes of the sun's magnetic field out to interact with the Earth and the Earth's magnetic field, and those are important too. All of these kinds of interaction turn out to be variable. They change with time, and the variations have different time scales and different levels of importance, and frankly, we understand them at different levels, and so we'll get a look at least some of this variation. Somebody please laugh. Thank you. Sorry, Sandra, I didn't know you'd be here. We have a lot of light that comes from the sun, right? I mean, it's an amazing amount. For those that are comfortable with the numbers, 4 times 10 to the 26 watts. That's what's known as the solar luminosity. I don't think it helps at all to say that that's 4 trillion 100-watt light bulbs, but that's another way to say the same thing. It's still an incredibly large number. By the time it gets to the Earth, it spreads out, filling the volume of space that the Earth's orbit sort of occupies. And that means that it works out to something like 1,300, 1,370 watts per square meter above the Earth's atmosphere head on. So if you put some sort of a collector that faced perpendicular to the rays from the sun, it would collect that much energy. Of course, different parts, even of the atmosphere, will intercept that at different angles, and so the amount that actually heats up something changes depending on where you are on the Earth and what time of year it is. And the surface of the Earth, of course, also experiences this. I like this picture of the Earth and then the moon, in part because it does show this day-night boundary of the Earth, but the orientation of the Earth's spin axis is not co-aligned with that unless it's an accident of timing for the image. The Earth's axis, as you know, is tilted 23.5 degrees away from the perpendicular to the Earth's orbital plane. Okay, so it sort of goes around the sun like this. Unless there be some misunderstanding, if the microphone is the sun, the Earth doesn't, first order, the Earth doesn't flop around. It keeps the orientation of that spin axis like I've got my fingers, and so that means that at different times, say for example here, sun's rays are spread out up here on this part of the Earth where, with my northern hemisphere bias, I say we live, and when it comes around over here, and we're tipped same way, pointed toward the North Star, the sun's rays are more direct further down. They're also, the sun is up longer in one hemisphere than the other for each one of those. Put those two things together, you need them both, and that explains the seasonal variation of the Earth's weather, climate. Climate would really not be varying that much because of that, because it's time average, but same idea. There's some other variations, too, that have to do with the fact that the Earth's tilt is not constant, neither in orientation nor in amount. The Earth's inclination varies, and it spins in a cycle. The one thing's called precession, and then there's various kinds of noddings that go on in the Earth's axis orientation. The other thing that changes that a lot of folks don't know is the actual shape of the Earth's orbit. It gets more elliptical and less elliptical with time. And if you put those things together, you can come up with terms that put us further away from the sun in northern hemisphere summer. That's where we are now, actually. Let me repeat that. Right now, the Earth is further from the sun in northern hemisphere summer. Distance got nothing to do with it, right? We're closer in northern hemisphere winter, and the variation in the two distances is reasonably small. The Earth's orbit is fairly circular. Okay? But there are times when those situations are reversed, and there are times when the squishiness of the Earth's orbit, the influence of other objects, makes it so that the difference is bigger in distance from one of those seasons to the other. So you throw all those things together, and those can lead to long-term variations in the Earth's climate. Those are the mechanism behind the so-called Milankovitch cycles. I'm not going to say much about those today, except there's pretty good reason to believe that sort of long-term variations, prehistoric variations in the Earth's climate, things like some of the ice ages and so on, correlate to some of those terms. Not all of it, and not every little fluctuation in that. Okay? But so we know that as much as we know anything prehistory, that there are interactions between the sun and the Earth that affect the long-term climate and so on. We'll come back to that later, though. On the other hand, for most of the time we've been studying the sun, let's say a few decades, maybe several decades, we're now pretty convinced that the solar light output varies by an amazingly small amount, 0.1% at most. And most of that variation occurs in this cyclic variation that we have due to the sun's activity cycle, an 11-year cycle that I'll refer to several times. So the sun's total radiative output is believed to change by around 0.1% total. At some wavelengths, though, it's a lot more. there's certain wavelengths where the sun emits light where we can have basically a doubling of the amount of radiation that comes from the sun in those wavelengths. Those wavelengths all told make up a very tiny part of the total radiative output of the sun, but some of them are important in different places in the Earth's atmosphere. And so that's going to be a complicating factor in trying to understand how these things combine. This is a graph that's surprisingly easy to understand and surprisingly difficult for them to have produced. I say that because when you first look at it, it looks kind of complicated. This is a graph of the variation in the solar output over time. You can see on it the markup there. It's 1%. Well, I'm sorry, the projection is changing it a little. See the 0.1% mark up there? So even the noise you see in the variations that are on there are pretty small. The black line is a time average. What's complicated about it is these, by the time I started to graduate school, folks are finally getting around to putting in space an instrument that was capable of measuring the radiative output of the sun accurately. Until that time, it was something you did from the surface of the Earth. It was not done well because even in a dry place, at the surface of the Earth, atmospheric transparency, variations in temperature effects could cause the sun's variations to be just swamped by non-solar effects. So they started putting instruments in space to do it. The bad thing was that different ones of those instruments had different calibration values. So that everybody agrees now that during times of high solar activity, high sunspot number, the sun is brighter. I'll come back to that. It's counterintuitive at first. The sun is brighter during periods of high sunspot number and dimmer at times of low sunspot number, but nobody could agree whether there was a longer-term trend that was being measured by these devices because they didn't know what their 0 points were. This is the best effort to date to match the 0 points of several instruments and put them together. There may have been a bias hidden in here, I don't know, but it looks like I read the paper close enough to know that they really tried hard to make sure these matched. And if you look at this, it looks pretty darn flat, right? This patient has a reasonably steady pulse and is not really seeing much change in the slope of this variation. Okay. You may read online something different. There's some things, well, you can find anything you want online. But I'll show you an example of that in a minute. But you may read online that the sun has been getting steadily brighter recently. This diagram says no, it hasn't. Okay, this diagram, now I realize it ends, just prior to now, but it's, basically it says no, it's not getting brighter. The sun's output has been reasonably steady, except for this 11-year cycle. Okay, just a quick tour through the different layers of the sun so we can understand a little bit about the effects that it has on us. The upper left picture shows what's called the solar photosphere. The vast predominance of the light that comes from the sun comes from this layer. When you put on those eclipse glasses and go outside and look at the sun, that's what you'll be looking at. Out of that 10 to the 24, 4 times 10 to the 26, watts of energy, the part that's not coming from that part is a tiny, tiny fraction of a decimal place in there. So most of the light from the sun comes from that layer. You can see in that image some sunspots. And the arrow on there, by the way, points to something we're going to look at more closely in a little bit, but just keep that in mind. In the upper right, we see actually the place where the arrow is, and we see the layer of the sun that's actually just a bit above the photosphere. It's lower density than the part that most of the light comes from. It's higher temperature, almost a factor of 2 hotter. It's a place where only certain wavelengths of light are very efficient at producing light or radiation. And so you can see certain kinds of activity in that layer that you can't see in the layer below. Okay, so we're going to see a lot of the variation. Some of the snazzy pictures you see of the sun come from that layer, not from the white layer below it. And then the bottom picture is the solar corona taken from a spacecraft. That's called a coronagraph. There's a disk blocking the sun. The white circle is actually about the size of the sun. And you see this thing around it. That's the inner part of the solar corona. Very low density, actually lower density than would make a great vacuum on Earth. Very high temperatures. Okay, the temperature in that part is around 2 million kelvins. I'll show you a kind of a really cool picture of it in just a second as well. Okay, light comes from these different layers, different ways, with different reactions on Earth. So here's the photosphere. Notice in the upper left a picture of the sun in the photosphere at the beginning of the last decade, with a lot of sunspots, more or less concentrated along the equator. 4 years later, the sun looks significantly different. No sunspots, or I think there might be one in the sort of bottom right you can barely make out. The sun is, in theory, dimmer on the right-hand picture than on the left. The fact that it actually looks like that is just an accident. Okay, the sun isn't really that much dimmer. It's just the way the image was produced. Down in the bottom right, there's going to be a little video that I'll play. So if you can't see it, I'll apologize for the podium here. This is a close-up view of the photosphere. Shows a very enlarged image of a sunspot. I'm going to start the little sequence here, and what it's going to show us are the motions that take place in the photosphere that then relate to the intensification of the sun's magnetic field, which is important for the other things. So let me push that. So the little shimmering you see in there, or the kind of boiling motion, that's the motion in the solar photosphere that we call convection, granulation specifically for this motion. And that moves around, and in that part of the sun pushes the magnetic field of the sun around, concentrating it to make things like the sunspot that we saw next to it. This is, by the way, is a Japanese and U.S. Collaboration called Hinode, I guess. If someone knows how to say it more correctly, I appreciate the information. I'm used to calling it Solar B, which is what everybody called it till it. You know they only name these things after they're successfully in orbit? It's true. It's true, which is a good rule, you know. This is the chromosphere. We'll look for some variations in this as we start it into rotating. So you see a couple of different things happening. Parts of the sun's rotating, right? This is a few days worth of data. The sun has layers, the chromosphere has layers that are brighter. They have impulsive events. There's material kind of blown off of the chromosphere and little things that fly off to one side or the other. Okay, so that's some of the kinds of changes that come in that layer. And I don't have a movie of this yet. I will in a second. This is a heavily, heavily processed of the solar corona image of the solar corona taken during a solar eclipse. It used to be the only way we could see the corona was during a solar eclipse. Moon blocks the disk of the sun, and the corona extends beyond it. This particular one, they really took a digital sledgehammer to this to make it look like this. I mean, I think all the sort of contours are real, but they're heavily exaggerated. Has anybody in the room seen a total eclipse of the sun? Oh, actually, yes. I should know. Believe it or not, I haven't. Okay, so. Yeah, really. And we've got 3 videos that or sequences I want you to watch. First of all, bottom right is the photosphere for a particular event. Okay, so these are all 3 going to show you the same event. We'll move down a couple slides and see the same event in other videos as well. So watch very closely in the bottom right, because it's going to be hard to see this. Keep your eye on the upper sunspot right around here. Oh, I pointed you to the wrong one. Right there. Last time I did this, I wound up going forward 4 slides, too. So let's see if I can make. Okay, here we go. Okay, just a little sort of a poof, right? Just gets a little bit of whiteness there. This is one of the strongest solar flares ever recorded, and that's the extent of its effect on the photosphere. A very, very tiny change in the total radiative output of the sun. Okay? On the other hand, in the chromosphere, it's a little more dramatic. So in the chromosphere, we see a region brighten, kind of an S-shaped thing, and then part of it lifts off the sun, right? Something that barely even registered on the photosphere. In the ultraviolet part of the spectrum, that would be a very strong signal. And the green image is an image of extreme ultraviolet. It's really showing the corona. Now, I apologize. I either had to put this on its own slide and make it big. What you're going to see, same place as that arrow was pointing before, right? Upper right part of the sun, watch, and then I'll go back and point out what's happening, because it's going to just go by like that. It's a faster time lapse. Boom. Okay, whoops, see, I knew I'd do that. Go back to, try it again. See if I can just make it stop and come back may or may not be shown. It shows up out of there. If you look really carefully, right up, there's a thing that looks like this. Some bright lines that go like that. That's because the detector that's detecting this was completely saturated for that location. Similar amount of output would have been in the X-rays. So in this case, in the X-ray part of the spectrum, this is in fact the largest solar flare ever recorded up until that time. This was in the early part of the last decade. There's been one recorded since then that probably was at least as big. But when they get really big, it's hard to know because they saturate your detectors, right? Okay, so we see three different manifestations of the same thing, all in light. Okay, so when I get to talking about what the light does on the Earth, we'll need to keep those in mind. Let me click ahead. Just a little bit of the particles. I'm going to rather show you the effects than go through all this. A lot of particles come off the sun. About 1 million tons of particles per second. Nothing, right? Amounts to 1/100% of the sun's total mass. Actually, the sun loses about that much matter just by producing the light that we get, so it's not a big deal. It's coming out fast, supersonically, at temperatures like the coronas, so 400 to 800 kilometers per second. And when we get these big blasts that I'm about to show you, they can carry a lot of mass. And those particles and the magnetic field associated with it can, under the right conditions, reach us. Okay, so let me do the top one first. Boom, right off to the same place, right? We're looking in the right. Let me replay that. There's a couple of, oh, I forgot it. Put that on a loop. So there, see it just like that. Goes off on the right-hand side of the screen. If I stop and measure it, it turns out that it's moving about 1 million kilometers in 16 minutes. Okay, so it's really booking out of there. If I click, stop that one. This is a bigger field of view. By the way, these little white things, right now, in this picture, those are stars. Okay, so the sun has been blocked out. The stars are showing from behind. This is a bigger field of view. We see the things, it's popping off every which way again. And at the end of the sequence, the white things, they're not stars, right? We didn't add stars. Those are the particles from this blast traveling the 92 million miles to the spacecraft, crashing into the spacecraft and causing the detector to react. Okay, so that, and this spacecraft is located at on a line between us and the sun. Okay? In the meantime, the magnetic field of the sun itself, we already said, produced by granulation, the motion in the photosphere, produced deep in the sun, intensified by the granular motion, and then it comes out in big blobs sometimes with that blast like we just saw. Said that. Well, that's not important for us. Okay, so you put all this together with the fact that the sun varies all of these things on about an 11-year cycle. This graph shows sunspot number, the zigzagged line, forecast for what sunspot number we're supposed to be the last cycle and what they may be the next cycle. And you can see that we're starting to see more sunspots. This solar minimum that lasted about twice as long as it was supposed to, complicating the climate change debate. And we'll come back to that in a second. You can see the sunspot number is starting to increase now, and in fact, I'll show you an image at the end of this that comes from today. Not so much about sunspots, but the sun is definitely more active than it was a while ago. Okay, so what happens here on Earth in reaction to all these things? Remember, we've got light, we've got particles, and we've got magnetic field. We want to think about how all those influence the Earth. Okay? All right, this is a picture of a graph of the temperature of the Earth's atmosphere. The part we live in, the troposphere, is that little tiny layer down at the bottom. And you'll notice that the temperature has a local maximum at the surface, and it decreases with altitude. Okay? Everybody who's gone up a mountain sort of expects that. Did you ever stop to think why it does that? After all, you're getting closer to the sun. Not much, right? And the answer is, well, the heat for the bottom layer of the Earth doesn't come directly from the sun. The sun produces it, but it doesn't come directly from it. It comes from the visible wavelengths of light heating the ground. The ground comes up in temperature and re-radiates the light as infrared radiation. That heats, that's absorbed by the greenhouse gases in the atmosphere, and that heats the lower atmosphere. But of course, the further you get from the surface, the further you get from the source, Also, the more transparent it gets for other reasons, and the temperature decreases. But when you go up above that, notice in the stratosphere, the temperature turns around and begins to increase, suggesting there must be some sort of a source of energy at that layer. The source there turns out to be the absorption of ultraviolet light by ozone. Remember when we were very concerned, a lot less concerned now, about ozone and ultraviolet light getting through to the surface of the Earth? Ozone up there absorbs the ultraviolet. So if you have a change in ultraviolet light from the sun, which we do, and we do in significant amounts over the solar cycle, you're going to change what goes on in that layer of the atmosphere, so-called stratospheric heating. The top layer of the atmosphere, now you get a little fuzzy about what you want to call atmosphere. It gets very low density, and in the meantime, we sort of designate a separate category, the ionosphere, is the place in the Earth where there's lots of ions, which happens to overlap with the atmosphere. The ions are produced by X-rays from the sun. So if you change the number of X-rays coming from the sun, you change the ionosphere. And anyone who does ham radio, shortwave communications, knows that in periods of high solar activity, it's much more difficult to communicate long distances around the Earth because you use the ionosphere to bounce your signals. And if you have more radiation, the ionosphere goes closer to the ground. Another example, I listen to WCBS going home from the observatory at night. Can't hear it in the daytime. And that's because the ionosphere is lower in the daytime because of the solar influence and higher at night. Okay, so the ionosphere is also directly impacted by relatively quick variations in solar output. Okay, so even though the total sun is very steady, these certain wavelengths affect the upper atmosphere of the Earth disproportionately if you think about the total amount of light from the sun. And I said everything probably on the slide. Oh, one last thing. When you heat the atmosphere, it expands. Right? Heat a gas, it will tend to expand. When you expand an atmosphere above which there are little tiny pieces of stuff orbiting, those little tiny pieces of stuff find their way into higher densities of the atmosphere, and things like low-orbiting spacecraft find their orbits perturbed, and ultimately their orbits will decay and they fall out of orbit. So the size of the Earth's upper atmosphere actually has an impact on spacecraft, and we'll come back to that in a second. I'll skip that climate one on purpose and come back to it in more detail. Okay, what about the magnetic field? Let's skip the upper left-hand picture for a moment. It's kind of a diagram of the Earth's field reacting to the sun. Let's look at the video in the upper right. The NASA video showing a blast of particles leaving the sun right about now, or now. A CME, coronal mass ejection, traveling out through interplanetary space, runs into the Earth, perturbs the magnetic field. The magnetic field sweeps behind the Earth, accelerates particles, and those particles smack into the upper atmosphere of the Earth, creating auroras, northern lights, southern lights. Okay? The bottom right-hand image is an actual spacecraft image. It's a composite of images showing what's called the auroral oval. If you think about yourself being located above the geomagnetic north pole of the Earth and looking down, that orange you see is the auroral oval. It's there all the time. The size and intensity of it changes with the amount of activity from the sun. So right now, if you took an image of this, it wouldn't be bothering us, or we wouldn't be enjoying it. But in periods of high solar activity, the auroral oval can spread down closer to where we are. That injection of particles into the upper atmosphere represents another source of heating for the upper atmosphere of the Earth. And so I guess I'm emphasizing that there are reasons to suspect that there are influences on things like temperature in the atmosphere due to solar activity, even though the sun's brightness doesn't change very much. I have to throw this last one in. If I'd have given this talk 3 weeks ago, I wouldn't have thought to put this in, but it turns out it's really important. There's something called the Forbush Decrease. Let me just skip ahead and I'll tell you what it does. Here's a graph of it. Here's what happened in this graph. This is actually from a cosmic ray detector in Moscow. Cosmic rays, primary cosmic rays, galactic ones, are particles produced out in the galaxy. They're way more energetic than the typical particles that come from solar activity. In periods of low solar activity, when the sun's magnetic field isn't doing much with us, those particles come in, scream into the Earth's atmosphere, wreaking havoc on the nuclear level, coming down in. One of the things they do is make other particles, neutrons, and this is a graph of the neutrons as a function of time. And one thing they do is produce carbon-14. carbon-14 varies in intensity with the cosmic ray flux. Magnetic fields from the sun, those big bubbles we saw blasting off, can protect the Earth from galactic cosmic rays and reduce the amount of galactic cosmic rays that come into the Earth, thereby changing the rate of carbon-14 production. It also changes, undeniably, charging of the atmosphere of the Earth, that is, positive and negative electrical charges. So the question that has come up recently is, what could that do? What could changes in charge do? Okay, so we'll come back to that. So, does this add up to stuff, impact on the Earth? Well, of course it does, or I wouldn't bring it up. We already talked about satellites, expansion of the Earth's atmosphere affecting satellites. It's a very real effect. Particles from the sun get trapped in the Earth's field, enhance our radiation belts. They have impact on people who spend a lot of time at high altitudes, certainly astronauts. At the solar maximum in roughly 1990, there were some astronauts in the space shuttle. In the space shuttle, you're inside the protective influence of the Earth's field, but they still had in their eyes little flashes of light that indicated that high-energy particles from the sun were coming into the vitreous humor in their eyes and producing what we call Cherenkov emission. Had to have been disconcerting, because it's basically just another form of ionizing radiation, something that we normally try to avoid large amounts of. If you fly polar routes in aircraft, you're also exposed to this, and airlines and the military keep track of the amount of particle flux coming in the poles in order to avoid sending people through too many cycles of that. A passenger typically wouldn't worry about it, but a crew member might. Passengers are expendable. And then the magnetic field of the sun shakes the Earth's magnetic field. And anybody who's had Physics 2 or Physics 112 should know that if you shake a magnetic field inside a conductor, you generate currents. And the Canadian power grid back in World War II was blowing up. They just put it in, and it was blowing up. And everybody, of course, thought that somehow spies are coming over and blowing up the power grid, and then they realized, oh, it's a period of high solar activity, and they didn't understand it as well back then, but we now accept that there's going to be a certain number of power outages caused by large fluctuations in the geomagnetic field due to the sun's magnetic field. Anything else that's affected? Well, it's problematic. This is my favorite one that I found. This is the Dow Jones Industrial Average plotted against time, and sunspot number plotted against time. Now, first of all, anybody who knows anything about finance knows that there's something funny about that Dow Jones Industrial Average. It hasn't been flat since 1825. It has steadily increased dramatically since 1825, so it's been detrended. Whenever you detrend data, you got to be really careful about what you're doing, because you can actually throw some baby out with the bathwater when you do that. Having said that, let's say I accept their detrending. I see no relationship between those two curves. They're okay. There's a couple of places where they sort of accidentally line up. This is from a website, I don't mean to make fun, called Financial Cycles Weekly, where some of the people who write are unabashedly writing about the importance of astrology in making forecasts for the Dow Jones Industrial Average and things like that. I think there's essentially no correlation between these two things. Having said that, if there was a correlation between climate and solar activity, climate influences other human activity, including agriculture, so there could be a connection, right? But there doesn't really seem to be. If this is the best somebody can do to show it, then I think they've got a little bit to go. Okay, on the other hand, the climate question. And Otto Muller, who's really in tune to this stuff, is going to know right away that these next two graphs are not really the graphs I wanted to show. But the graphs I wanted to show are so complicated that I just gave up and put these in their place. And they show sort of the same thing. There have been some suggestions over the last decade in particular that there actually is a correlation between enhanced output of the sun of some sort, I'll come back to the some sort in a minute, and the global increase in temperature. So the two graphs you see in this case, the top one shows sunspot number as a function of time. The bottom one shows global mean sea surface temperature as a function of time. And wow, right? They look like they go together. This and some more detailed studies have led some folks to guess that about a third of the temperature change that we attribute to, that we call global climate change, that some folks want to attribute to anthropogenic causes, human causes, a third of that, some people say more, is attributable to what we call the solar forcing term. The guy who did the really interesting work on this is Svenmark. And the graph that he would have had me put up here, but there are 4 of them, would be one relates to this Forbush decrease, where he says, all right, we have enhanced production of carbon-14 when the sun does not shield you from it. So low solar activity of more carbon-14. More carbon-14 is indicative of more cosmic rays. More cosmic rays charge the atmosphere. Charged particles form the basis for accumulating droplets to make clouds. You make clouds, it's not a clean call, but clouds tend to reflect more light out into space than they do trapping infrared in. And so if you had periods of low solar activity, you would expect, by his model, lower temperatures. And then he made some graphs where he used the length of the solar cycle as an indicator of the strength of this effect. And when he did that, he found a correlation that looked very much like these, which is to say that the length of the solar cycle had increased in a way that allowed us to say the temperature should also increase. And it matched the climate change model pretty well. Okay. Of course, no one's going to let that kind of thing go unchallenged, and some people went and looked at it. Again, this isn't quite the graph I wanted to show, but there's someone named Lockwood, and I inadvertently left his name off of here, who says that the way Svenmark determined the length of the solar cycle was wrong. I've read that paper all the way through. When he comes up with a system for determining the sunspot number, and then when you determine the sunspot number, you determine how long the sunspots have been above a certain value, determine the length. When he runs his data, it looks more like this irradiance data, which is to say the temperature increases, that's the red line, but the solar term flatlines or turns down a little bit. So his argument is that maybe in the past, where those two curves come together, there may have been a solar forcing term that was behind it. But since that time, more in the last 20 years, some other term, and he argues the anthropogenic greenhouse gas effect, has caused a parting of those two, and you can no longer blame the sun for any part of that. And of course, they're finding it out. They're not doing it particularly well. I've read rebuttals by both of them. I'm probably showing my bias here, but Svenmark's really are some of them are kind of low blows. I think he strikes me as a little bit of a rogue, and I think he shoots from the hip a few times in some of the things. So I'm dwelling on this because this is in the news now. This is people fighting this out about you're ignoring the sun. No, we're not. The sun isn't doing this. And when you start making decisions about what to do with climate change, this has to be factored in, right? If you don't really understand the forcing term from the sun, you have an issue. On the other hand, if you do understand the forcing term from the sun, at least well enough, then you have a different issue, right? And so that's kind of where this is kind of standing now. I think more people in the climate business certainly are like this graph and fewer like the previous graph, okay? Okay, so I talked through all that. Okay, so why do we care about this stuff at all? First of all, I'm a solar physicist. I love the sun. It lets me have daytime hours when I'm doing research as opposed to the nighttime stuff. So that's one reason. But so we have to sort out the impact of this solar-terrestrial interaction on Earth's climate. The technological impact, when we go into the next maximum, folks, I think you're going to hear about this for something that goes wrong in your life. Something, a communication satellite, some other, mostly forms of communication, or people being upset about a particular satellite falling in a place and they're worried about it's going to fall on something or bring something like nuclear energy. I don't know if there's any former Soviet satellites still doing that, but the Soviets used thermopiles, nuclear stuff, when they built their spacecraft. And so when they fall out of the sky, people really don't talk about not in my backyard. You know, please don't put a crater in my backyard filled with nuclear material. The power grid, especially in the northern area, our area, Canada, geomagnetic pole is close to us, actually. It's not at the Earth's spin pole. It's closer. And so that means we're more vulnerable in this part of the world than they would be, say, at a similar latitude on the opposite side of the world. So that's part of the issue. And, of course, especially when we start talking about, it wouldn't be this cycle, sadly, when we talk about making long trips in spacecraft. This is something that's going to have to be dealt with. If you go to Mars in a spacecraft, the activity, the particles, the stuff coming from the sun, you don't want to be hanging out there, even in a halfway decent spacecraft, when a blast of these particles comes by. So people come up with elaborate means of shielding themselves. The one I like best is crawling in a tunnel with water around it, because you need the water anyway, as a way of shielding themselves as they travel to Mars unprotected. By the way, Mars isn't going to protect them either. Mars doesn't have a good magnetic field, so they'll have to worry about it there too. So there's all these other things, but the best reason, of course, is it's really cool or hot. This is the sun today. This is what the sun looked like in, I'll call it X-rays. It's really very long, a very short wavelength ultraviolet. It shows the corona. It shows a region of active features along here. That shape is indicative of us moving along pretty well into the process of the solar cycle. What we'll see is that with time, as these active region latitudes will begin to move toward the equator, and then they'll dissipate. And then the whole process repeats itself. And I won't get into the rest of it because I love talking about it. But I want to give you a chance to ask some questions, or Otto will probably make some comments. But so questions? Yes, Emerson.